Hello. Today we are going to start our new lecture on some current trends, that how we are going to modify our nanocomposites, or rather how we are going to modify our samples so that we can use those nanoparticles and we can get some better properties. If you remember, in our last some quite previous lectures we have already discussed about that how to modify the coatings, how to modify the nanofillers, but here the main aim of this particular lecture is to not to modify the nanocomposites, just to modify the nanofillers first, then that modified nanofillers we are going to use, or maybe we are going to coat onto the substrate material. So the topic of this particular lecture is depends on the current trends in surface modifications of nanomaterials. So whatever we are going to discuss in this particular topic, that current trends means that recent, maybe from 2013 or 2014 this technology has been started, and that technology we are incorporating to modification of the surface engineering. So first, current trends for surface modifications of nanomaterials. So basically there are three techniques generally we are adapting. Actually not there are three techniques, there are so many techniques, but all these techniques has been classified into three broad spectrum. One is called the doping, another one is called the functionalizations, another is called the others. Others means some kind of polymerization methods or maybe some kind of other modification methods. So today in this particular lecture only we are going to discuss about the doping. So here we have seen so many figures that somewhere we are using some kind of graphene hybrid nanomaterials, somewhere we are using some carbon nanotubes or maybe some carbon dots or maybe graphene nanoribbons, and we are trying to modify. So till today actually we are discussing that how we are going to modify these materials, or maybe how we are going to do modify these materials with some nanocomposites, and we are trying to prepare the hybrid nanocomposites. But actually today we are going to do that how that structure, not the chemical structure but the physical properties of this material can be changed by applying any kind of impurities or maybe inserting any kind of impurities or maybe the doping materials inside this structure. So first, before going to start that what are the going on about the doping, first let us know that what the doping means. So actually the doping means that we are trying to insert some kind of dopants or maybe the impurities inside some materials or maybe some crystal structure of a particular nanoparticles. So when we are doing, generally we are having some limitations. So when we are inserting these impurities less than 1%, that time only we are calling it as a doping. If the loading percentage will be more than the 1%, then it will be categorized into some other forms. So here the doping intentionally introduce impurities that is less than 1%, already I have said you, into an extremely pure intrinsic semiconductor for the purpose of modulating its properties. So here this is the carbon structure in which we are introducing the nitrogen atom over there, and this atom percentage is less than 1 of the whole carbon percentage. So here that is why it is known as the doping. Then last previous lectures also we have discussed about the coating. So once again just give a glimpse of that, or maybe give a just idea that what is coating means. So a coating must adhere to the only one substrate. A coating once applied is exposed to the elements and must withstand the abrasion, marring, solvents, water and heat. So simple, I am having the substrate, that substrate will be covered by some kind of materials, either it can be the virgin materials or maybe it kind of some kind of composite materials, and that is known as the coating. And then when we are talking about the composites, so composites is nothing but it is a mixture of 2 to 3 elements or maybe the 2 to 3 materials. Then we are making certain kind of slurry type of mixture or maybe that concrete type or mixture of different materials, and then either that material directly we can use for some other applications, or maybe that material we can put onto the substrate material for better physical properties. So here the composite material is a material made from 2 or more constituent materials with significantly different physical or chemical properties that when combined produce a material with characteristics different from the individual components. So here you can see that there are several colors like blue, yellow, grayish. That means the layer by layer they are making certain kind of structure. Either this material directly I can use, or maybe this material I can coat onto the substrate material for any other properties. Now let us know that why we are doping actually. What is the main purpose of doing this kind of doping? So the main aim of this doping to increase the electronic properties or maybe the semiconductor properties of that particular material. So that is the main motto of this doping technology. So again we are going into the details. So first let us know the doping. So as I told already, doping is the process of adding some impurity atoms or replacing the host atoms in the semiconductor. So generally when we will go into the classification of this doping, we will elaborately discuss that how it is going on. Actually either one atom of that particular material can be substituted by that doping materials, or maybe the doping material can go into the interstitial site of that particular material. So by these two methods we can do the doping. These impurity atoms are known as the dopants. So what we are injecting inside the material, that is known as the dopants. After addition of these dopants, some of the properties of the semiconductors can be changed as per the requirement. So how much quantity the material I am inserting, but it should be more, less than the 1% of whole, depends upon that how much semiconductor property is going to be enhanced. So here the right hand side we have given a single layer graphene structure. So in which the top of this that the conduction band and the below is the valence band, and in between that Fermi level is actually staying. So when it is going towards the conduction band, generally we are calling it as a n-doped materials, and when it is going to the valence band, then we are calling it as a p-doped materials. But generally Fermi level is staying in between these two. Then same thing when we are talking about the bilayer graphene also, Fermi level can also go to the valence side or maybe to the conduction side. So now we have to discuss about some basic conditions that are required for the doping process are given below. So what are the conditions? Because it is not like that I am bringing some materials or I am taking some materials and by some chemical means just I am getting the reactions in between these two and one metal or maybe one atom will be inserted into the another one. No, of course it is not like that. There should be some specific conditions. That specific conditions should be met by that material so that doping can be done. So first one is that the atom which is to be doped in the crystal must be placed at a position same as that of the position of the semiconductor atom. So when we are talking about the substitutional doping, so just one atom from the parent material will be replaced by the another atom. So the crystal structure of that particular base or maybe the parent material will not be changed, only it will be replaced by your impurities. Number 2 will be there should be not be any distortions in the crystal after insertion of the dopants. So when I am talking about the parent body, when I am inserting some dopant or impurities into the parent body, the whole crystal structure of the parent body should not be changed. Only it can some molecules can be interchanged by the impurities material, or maybe that impurities material can go to the interstitial side actually which is vacant inside the parent material, but overall the crystal structure of the parent material is not going to be changed. Now the number 3rd will be the size of dopant should be exactly same at that of the size of the atom of the crystal. Yes, of course, because otherwise if the size of the crystal structure atom will be changed, then automatically the crystal structure will be distorted. Maybe there is some kind of vacant site will be created, then the overall parent body crystal structure will be changed, but that is not possible by this doping technology. So doping technology means the crystallite size of both the parent material and both the doping material should be same. And the number 4th and the last is that in a crystal the percentage of doping should not be more than 1%. So that is the vital parameter, because every material, every thing is having some receptibility capability. So more than 1% that material will not allow inside it. So always the doping material should be below 1% on the parent body. Then we are going to discuss about the types of doping. As I told already, there are several types of doping generally by, or maybe it's rather some kind of synthesis process by which we are doing the doping on our materials. So first one is called the according to the position of dopant in the crystal lattice, which is nothing but the interstitial doping. So first doping techniques is known as the interstitial doping. So from the name itself you can understand that whatever the impurity materials we are adding into our parent material, that is going to the interstitial side, because the overall crystal structure of that particular parent body is not going to be changed. So where this doping material will go, actually that doping material will go to the interstitial side of that particular parent body. So the dopant atom is not incorporated into the crystal lattice but resides between the crystal atoms on an interstitial site. For metallic materials that have relatively high atomic packing factors, the interstitial positions are relatively small. Yes, of course, because when you are talking about the metallic particles or maybe some metals, they are very closely packed. So getting the interstitial site is very difficult, or maybe less number of interstitial site is available. So that time the doping of that particular metallic materials is quite difficult. Next, atomic diameter of an interstitial dopant must be smaller than that of host atoms. Normally the maximum allowable concentration of interstitial dopant is low, less than 10%. So here we have given some kind of classical examples. So examples here, the carbon 2% concentrations from an interstitial solid solutions when added to the iron. So atomic radius of the carbon is 0.071 nanometer, which is less than the atomic radius of iron, that is 0.124 nanometer. So here you can see that when we are using this kind of structure, so simple the carbon is going into the interstitial side of the iron structure. So that means that here the interstitial doping is taking place. Here are also some kind of classical examples. When we are doing the manganese doping into the zinc oxide, still the manganese is going to the interstitial side into the zinc atoms, and here also for the aluminum was doped at interstitial side in zinc oxide, simple the aluminum atom is going into the interstitial side of the zinc oxide atoms. So that's why here just we are trying to show you that how the interstitial doping is taking place inside the materials and what are the conditions behind it. Next we are going to discuss about the substitutional doping. So incorporations of the dopant atom into the host atom which has an atomic interchange, and for stable structure you need change atoms no more than plus minus 15% of difference in their ionic radius. So the radius of those that impurities and the parent body atoms should not be variation plus minus 15%. So it should be almost same, then only the substitution can be possible. So the other important parameters for the substitutional doping, only this is the prime considerations, that the radius of both the atoms more or less same. Then the second one is called the electronegativity. Electronegativity means electropositive one element and more electronegative the other, the greater is the likelihood that they will form an intermetallic compound instead of a substitutional solid solutions. So this is the another conditions for this kind of doping. Next one is called the crystal structure. The crystal structure of metals of both atoms types should be the same. And the third one is called the relative valence of participating atoms. Other factors being equal, a metal will have more or of tendency to dissolve another metal of higher valency than one of a lower valency. This is also another prime factor which I will show you by giving some examples. So here we have given one examples about the nickel substituted into the copper materials. The atomic radius for copper and nickels are 0.128 and 0.125 nanometer respectively. Both have the FCC crystal structure. Their electronegatives are 1.9 and 1.8. But this is the prime factor. Valences are +1 for the copper and +2 for nickel. That means the valency of this nickel is much higher than the copper. So automatically when we will try to do the substitutional doping, the nickel will go inside the copper. That means the nickel will be here the dopants and the copper will be the parent body. So the main criteria of this kind of doping is that whose valency band or maybe that valency will be higher than the another, then that will actually inserted inside the body. So, that is the main criteria, that means the nickel substituted into the copper, not the vice versa. So, here also we have given certain kind of examples, that is called the N-doped graphene and the means nitrogen doped graphene and the B-doped means boron doped graphene. So, in N-doped graphene actually what is happening, atomic radius of carbon and nitrogen is equal to 70 pm and the 65 pm, both have the HCP hexa closely packed crystal structure. Electronegativities are 2.55 for carbon and 3.04 for nitrogen, and valencies are +3 for carbon and the +3 +5 for nitrogen. It means nitrogen substituted into the graphene because nitrogen is having more valences than the carbon itself. So, here when we are talking about the pristine graphene, its crystal structure is looks like this. When you are talking about the boron doped graphene, simply boron is doing the substitutional doping inside the carbon structure or maybe the inside the graphene sheet, and that is known as the p type. And when we are doing the nitrogen doped graphene, simply nitrogen is doing the n type, because why it is called the B doped graphene means atomic radius of carbon and B is 70 pm and 85 pm, both have same crystal structure. Electronegativities are 2.55 for C and 2.04 for N, but valencies are +3 for carbon and +3 and +2 for boron. So, that in that particular case the doping of boron inside the pristine graphene is very difficult, because more or less the boron valencies is less than the carbon. But if it will be equal, then that time either carbon can go inside the boron or maybe the boron can go inside the carbon itself. So, according to electronic band structure, there are two types of things when we are talking about the electronic band structure. So, we can classify these things into two types, one is called the p type semiconductor, another is called the n type semiconductor. Then what is the reason behind it? So, p type semiconductor, when it is doped with an element with one less valence electron, then the element it replaces, a p type semiconductor has more holes than the electrons. So, this is the prime factor that by which we can say that whether our doping is p type doping or maybe the n type doping in terms of electronic band structure. Then when we are talking about the n type semiconductor, when it is doped with an element with one more valence electron than the element it replaces, an n type semiconductor has more electrons than hole. So, for n type the electron density will be more than the hole density, and for the p type the hole density will be more than the electron density. Then here are the some classical examples, that examples of an n type doping. So, silicon is from group 4 and has 4 valence electrons, phosphorus is from group 5 and has 5 valence electrons. So, automatically the phosphorus will go inside the silicon, because the phosphorus valency is more higher than the silicon. So, when silicon is doped with phosphorus at room temperature, there is an extra electron, since P has 5 valence electrons. The extra electron has very low binding energy and this bond is very easily broken. When the bond is broken, the extra electron is free to conduct, this extra electron is free to conduct and P becomes positively charged. In this case, electrons are created without creating additional holes, therefore, the semiconductor becomes the n type, because in the n types the electron density is more than the hole density, and the opposite case is taking place in these particular examples when we are doing the p type doping. So, silicon is from group 4 and has 4 valence electrons, aluminum is group 3 and has 3 valence electrons. So, when silicon is doped with aluminum at room temperature, there is a missing electron, that is called a hole. A neighboring valence electron can take the place of the hole. When this occurs, aluminum becomes negatively charged and the hole moves to the neighbor atom. In this case, holes are created without creating the additional electrons, therefore, the hole density of that particular material is more, and that is why that semiconductor becomes the p type semiconductor. Then here is also we have given some examples that on n-doped semiconductor and p-doped semiconductors. In n-doped semiconductors, which is also known as the pentavalent dopant, there is an electron in the crystal which is not bound and therefore can be moved with relatively little energy into the conduction band. Thus, the donator energy levels close to the conduction band edge, the band gap to overcome is very small. And for p-doped semiconductor, which is known as the tetravalent dopant, a hole is available which may be already occupied at low energy by an electron from the valence band. Thus, the acceptor energy level is close the valence band. So, here the same thing we have given in some schematic illustrations. So, this is known as the intrinsic semiconductor, where I am having the conduction band and I am having the valence band, and in between is known as the band gap. So, when we are talking about the donor n type, so automatically the hole is density is more in that particular case. So, that is why in that particular case the electron density is getting more. So, that is why it became the n type, extrinsic n type. But when you are talking about the p type, the hole transportations is more, so hole density is going to be more. So, that is why it is coming onto the p type semiconductor. So, here all are the some examples, rather some of the gathered literature review what we have observed, and the right hand side we have given that in which year the scientist or people has done this kind of research. So, first is called the PBTEC, which is the dopant is known as the thallium. Here we have done the substitutional doping, property enhancement, thermoelectric properties has been enhanced. It has been done in the year of 2016. So, when we are doing by the chitotions, we are using the dopant like zirconium oxide, and the property enhancement is mechanical and antibacterial properties. It has been also done in the 2016. When we are using the reduced graphene oxide, we are using the dopant as a boron, and that is also the substitutional doping, as I told already, because boron doping is known as the substitutional doping, and it is enhancing the electrochemical properties of that particular material. It has also been done in the year 2016. When we are using the tungsten oxide, then nickel doping is taking place, that is known as the interstitial doping, because nickel is going into the interstitial side into the composite materials. So, which is known as the electrochromic, and it has been done in the year 2016. Same thing when we are doing the reduced graphene oxide with phosphorus and cobalt co-doped materials. So, it is going on to the interstitial doping. So, it is known as, it is enhancing the electrocatalytic properties of that particular material. It has also been done in the year 2016. So, from this year you can get the informations that doping is the latest technology which has been invented maybe 1 year back, and the people are extensively used or maybe the modifying the material filler properties or nanoparticle properties, so that give or maybe so that it can enhance some better physical properties. Here is also the same thing of continuation of the last slide, that is multi-wall carbon nanotubes. It has been doping by the nitrogen. It is also one kind of substitutional doping. It is increasing the physiochemical properties. It has been done in the year 2015. Then TiSe2 chromium has been used as a dopant materials. Substitutional doping has been done. It is increasing the magnetic properties. In the year 2015 it has been done. Then titanium oxide, that nitrogen doping has been done, either it may be interstitial and the substitutional side. Then optoelectronics properties of that particular material is getting increased, which has been done in the year 2015. Then graphene, that is also one kind of promising materials as in the field of nanotechnology, where we are doing the doping of that graphene by nitrogen and sulfur co-doped. It is also one kind of substitutional doping, mechanical and electrochemical properties is getting enhanced in the year 2015. Then we are doing also the modifications of reduced graphene oxide, and fluorine and nitrogen co-doped has been taken place. It is also one kind of substitutional doping. The photoluminescence property of that particular material has been enhanced in the year 2013, and here also the another one, that graphene, it has been done by the boron and nitrogen. substitutional doping has been taken place, the electrochemical properties of that particular material has been enhanced in the year 2011. So what I am trying to say is that this doping technology is the two latest technology that people are trying to use, or maybe that maximum people is using from last 2 to 3 years. Then here also we are trying to give certain examples, that preparation of boron doped graphene. So here the firstly boron oxide or maybe that boric acid and the graphene oxide in a mass ratio of 1:2 were mixed and ground. Then the mixture was annealed at 1200 degrees centigrade for 4 hours. The oxygen containing groups grafted on the graphene surface are thermally unstable, which are eliminated in the annealing step. The removal of oxygen species result in some active sites that simultaneously react in situ with boric acid, resulting in the boron doping into the graphene. After that the mixture was refluxed in 3 mole sodium hydroxide solutions to remove the residual boric acid, yielding the product of boron doped graphene. So actually what we are doing, first we are trying to make the graphene oxide, but graphene oxide there is so many materials are attached, like amine groups or maybe some kind of acid groups are attached. So first we have to annealing that materials so that that groups can be removed from the graphene side, and then that area or maybe that zone will be taken care by the boron atom itself. So that is why we are doing the substitutional graphene of boron into the graphene sheet. Then advantages of boron doping over pristine graphene. Boron doped graphene has a lower conductivity, hole mobility was estimated to be 550 centimeter square per volt per second at 7.5% boron doping with respect to pristine graphene, probably because of the presence of defects induced by the doping procedure. Boron graphene nanoribbons have been widely studied because of their potential to exhibit a tunable band gap for the semiconductor industry, which could be used for more versatile applications in microelectronics. Transport properties of boron doped nanoribbons indicate that the transmittance is strongly dependent on the spin state, whereas on pure materials is spin degenerations. So these all are the advantage for which we are making the boron doping onto the pristine graphene. Then another examples we have given, that we are doing the nitrogen doping into TiO2. So here this is the solution based approach to the synthesis of NTiO2 nanostructures. Generally NaNH2 was used as a precursor because based on colloidal chemistry, where the nitrogen concentrations and the dopant host lattice environment are controlled. To manipulate the dopant environment between interstitial and substitutional while accessing nitrogen concentration ranging from 2 to 70 in atomic percentage. So here the doping can be done by both the methods, either maybe the substitutional or maybe the interstitial, but it depends upon the loading of the nitrogen concentrations at the time of reactions. So what are the advantages? An improvement in the photocatalytic activity because of its stronger absorptions, the highest actual nitrogen doping percentage and the lowest photoluminescence efficiency. The high catalytic efficiency of the former can be attributed to the small crystallite size, high crystallinity and intense light absorptions in the visible light regions. So these all are the added advantage or maybe that added properties which we are getting by doing this kind of doping onto the titanium dioxide. Then here also we have given another examples, that preparation of the cobalt-doped zinc oxide and properties enhanced with the doping. So cobalt-doped zinc oxide nanoparticles were synthesized using co-precipitation method, in which the copal acetate dihydrate was used as the precursor, actually which is giving you the cobalt atom at that particular point. So here through this UVB spectra we have shown, we are trying to prove that if we are trying to increase the cobalt percentage, how it is affecting onto the doping. Then we are showing some kind of photoluminescence spectra. So if we are increasing the percentage of the zinc oxide, then how it is affecting onto the photoluminescence spectra, and same thing is we are getting from the magnetic characterization also. So when you are talking about the optical, the UV emission peak of cobalt-doped zinc oxide samples exhibit a large blue shift from 410 to 390 nanometer. Photoluminescence, the UV near band emission wavelength was found to be redshifted for cobalt doped zinc oxide compared to pure zinc oxide from 361 to 340. Magnetic, pure zinc oxide exhibits diamagnetic behavior, where cobalt doping in zinc oxide makes the samples ferromagnetic at room temperature, and magnetization values are increased with the increase of cobalt concentrations. So, simple, by doing the cobalt doped into the zinc oxide, we are enhancing its optical properties, we are enhancing the photoluminescence properties, not only that, we are enhancing its magnetic properties. So, by doing a simple single doping by the chemical route, we are trying to enhance this kind of properties of that particular material. Then now we have come up to our last slide, which is nothing but that it will give a glimpse of total lecture, that what we are going to discuss, or maybe what we have discussed in our previous slides. We have studied various new trends for surface modifications of the nanomaterials. Yes, of course, mainly we have discussed about the doping technology, how we are doing the doping. Dopants chemically adhere to the nanomaterials, due to which it results in huge improvement in electronic properties, which help for the development of ultra small and fast electronic devices. Synthesis of various doped nanomaterials have been reported, which shows enhanced properties with the doped nanomaterials. Properties of boron doped graphene, N doped titanium oxide, cobalt doped zinc oxide have been shown to observe the effect of doping of different dopants in some demanding nanomaterials. So, actually in this particular lecture we are trying to establish the doping technology, and then by giving so many examples we are trying to establish that how the doping is actually changing the material properties, by which method we can do the doping, what are the classifications or maybe the divisions of that particular doping technology, and then how we can make the samples, how we can prepare the samples for showing the different properties, and not only that, how the doping is improving our material characteristics. Thank you.